This lesson is about division of polynomials, remainder, and factor theorems. For any two polynomials p of x, let's say p of x is of degree p, and d of x, let's say the degree of d of x is d. As long as d is smaller or equal p, then we can perform division p divided by d. This division can be performed by using long division algorithm and using results of this division, for example the quotient polynomial q and the remainder polynomial r, we can rewrite the original polynomial p of x as a product of divisor polynomial times the quotient plus the remainder. What can we say about the degree of the remainder r? Well, if the remainder has degree r, it has to definitely be smaller than the degree of the divisor, because otherwise we would fit some of the divisor inside the r. So we can claim that r must be smaller than d. The remainder polynomial must be of lower degree than the divisor polynomial. What can we say about the degree of the quotient? Well, if the degree of the divisor is d, and the degree of the original polynomial is p, then the quotient must be such a degree, q, then when added to d, it gives you p. Why? Well, because when we multiply polynomials, then the highest exponent will be obtained by multiplying the leading terms, which are of degree d and q. So if we multiply x to the d times x to the q, we are going to add the exponents, and d plus q will give us p. So the degree q is such that d plus q equals p. Let's recall the long division algorithm using this particular example. So we are dividing fourth degree polynomial by a second degree polynomial. The rule is we are looking at the first term of the divisor and trying to fit it into the first term of the dividend. So x to the 4 divided by x squared is x squared, and we record this fact at the top of this division sign. Then we multiply back x squared times the divisor and write it under. So we'll have x to the 4 minus 2x cubed plus x squared. Next, we need to subtract whatever we divided out to find out how much is left still to divide. Therefore, when you subtract, we need to put a bracket. Since we prefer to add rather than subtract, this minus really means that we have to switch signs into opposites. So this minus will become plus, and that plus will become minus, and then we can simply add the like terms. So x to the 4 is subtracted, and that's what we expect. We should not have anything on the first term. Then x cubed plus 2x cubed is 3x cubed. Negative 10 minus 1 is negative 11x squared. And we should drop the next term, negative 6x. The whole algorithm starts all over again. So we're asking ourselves how many times x squared goes into 3x cubed. Well, that goes 3x times. And we multiply to check how much was divided. So 3x cubed minus 6x squared plus 3x. And we place a bracket around and we subtract. This causes that all the signs will be reversed, and we are adding with the new signs. Therefore, this is gone. Here we have negative 11 plus 6, so it's negative 5x squared. Negative 6 minus 3, negative 9x, and drop the last term, negative 4. One more time, x squared goes into it negative 5 times. Negative 5 times the divisor is negative 5x squared plus 10x and minus 5. Again, we place the bracket around and subtract. After subtraction, this is gone. This is negative 9 minus 10, so it's negative 19x. Negative 4 plus 5 plus 1. So, since this polynomial is already of lower degree than the divisor, which is second degree, therefore we can't really fit x squared into the remaining polynomial. So whatever we have here, this is our remainder. So here we have a quotient. This is our q of x. And the remainder r of x is actually not just a number, but a first-degree polynomial, negative 19x plus 1. So as you see, we could write the original polynomial p of x, which is this dividend, as the product of d of x, which is our divisor, this is our d of x, times the quotient q of x plus the remainder r of x. And in our case, the degree of the original polynomial is 4, the degree of the divisor is 2, the degree of the quotient is 2 as well, and the degree of the remainder is 1. So 2 plus 2 is 4, and 1 is smaller than 2. Since in mathematics we'll quite often need to divide by a polynomial of this type, first-degree polynomial, just simple x minus some constant, we would like to shorten the division algorithm, and such shorter version of division is called synthetic division. Let's observe the method of synthetic division in comparison to long division algorithm. For example, we would like to divide the third-degree polynomial by x minus 4. So if we write this in long division form, we need to replace the missing term is the linear term, there is no x's here, by a zero term, so 0x. The zero term works similarly as 0 in regular numbers. It's just a placeholder that will help to line up the same exponents. So let's go through the long division. X goes into 3x cubed, 3x squared times. We multiply, so it's 3x cubed minus 12x squared. Bracket around and subtract by changing the sign and adding. So negative 2 plus 12 is 10x squared. Drop the 0x even though it's 0. And again, x goes into 10x squared, 10x times. Multiply, so it's 10x squared minus 40x. And then bracket around and subtract, which will cause that this is positive sign and we are adding 0 plus 40 is 40x, and drop the last term, negative 150. X goes into 40x plus 40, and when we multiply we get 40x minus 160. When we subtract, that becomes positive, and our remainder end up to be just 10. So how can we see this in a short division? Well, first of all, we're going to write only coefficients of the polynomial. So instead of entire polynomial, we'll write 3, negative 2, 0, negative 150 under the division sign. And then in front, we are going to use opposite number to whatever we see in this divisor polynomial. So it's x minus 4, we're using 4. Divide by 4. That will accommodate for change in sign. We don't have to worry about switching signs when we subtract anymore. So after setting up the question, leave one line empty, underline, and the method goes like this. We are dropping the 3, we are multiplying the 3 times 4 to get 12 and write it here. So you can observe that this 12 is the same as that 12. Now we're adding them. This 12 is already with change sign. It's positive 12, right? The reason why it's positive is because we multiplied 3 by positive 4 rather than negative 4. So we add them like we did before. So we end up with 10. And again, we multiply 4 times 10 to get 40 and write it in the next column. The 40 that we see here is the same 40 as we had over there. We're adding 0 plus 40, leaving 40 again, and multiply by 4, which is 160. As you notice, the 160 is over there. Now we're adding the final two numbers, and the remainder becomes 10. So the last number is your remainder, and those numbers in front, they are actually coefficients of the quotient. Well, notice that the 3, 10, and 40, those are the coefficients of the quotient. From this calculation, to recover the quotient polynomial, we cut off the last number, that will be our remainder, and the rest of the numbers we read from the right to the left. The first number from the right is your free term, the second is the coefficient by the linear term, the third is the coefficient by the square term, and so on and so forth. If there is more numbers, it will be coefficient for x cubed, for x4, and so on. So that's how we read the information from synthetic division. Okay, let's practice one example. We can use synthetic division. First, we are listing all the coefficients, except that there is a missing term, which is x squared. So we have really 0x squared here, which needs to be indicated. Okay, let's list the coefficient in order: 1, -1, 0, 2, and 3. Then draw the division sign. And we're dividing by the root of this divisor polynomial, which is opposite sign to whatever you see in the bracket. So it's really -3. We divide by -3. This is the root of this polynomial. So now we underline everything, leaving one row empty. We drop the first number, which is 1, multiply by -3, write in the next column, and add the next column, which gives you -4. Multiply again, that will be 12, add with 0, which is 12 again. Multiply by -3 is -36, plus 2 it's -34, and when we multiply again, we end up with 102, and after adding is 105. So how do we read the answer from this synthetic division? We cut off the last number, and we are saying the quotient polynomial from this division is actually, that's a free term, linear term, second degree, third degree term. So it's 1x cubed minus 4x squared plus 12x minus 34. And the remainder from this division is a constant number, 105. Notice that we can actually write that the polynomial x to the 4 minus x cubed plus 2x plus 3 is equal to the divisor, x plus 3, times the quotient, which is this one, x cubed minus 4x squared plus 12x minus 34, plus the remainder, which is 105. Or equivalently, we could say that x to the 4 minus x cubed plus 2x plus 3 divided by x plus 3 is equal to x cubed minus 4x squared plus 12x minus 34, that's our quotient, plus 105 was still not divided by x plus 3. So we can express the quotient that way, plus some remainder, or we can rewrite that the polynomial is the divisor times a quotient plus a remainder. Generally, when we divide a big polynomial p of x by a linear polynomial x minus c, then we can rewrite p of x in the form x minus c times some quotient plus a remainder, and obviously this remainder must be of lower degree than 1. Therefore, it must be a constant number. So if we look at this equation, what can we say about the value of p of c? Well, if I plugged in c instead of x, then I really have c minus c. That means this becomes 0. Therefore, the p of c will be equal to just r. And that's actually a very powerful observation. P of c equals the remainder. This is actually called the remainder theorem. So the remainder in the division of a polynomial p of x by x minus some constant equals to the value of this polynomial at this particular constant. The conclusion from the remainder theorem is called factor theorem, and it refers to observing the zeros of polynomial p of x. So a constant c is a zero or a root of a polynomial p of x if and only if p of x is divisible by the linear polynomial of the type x minus c. Well, how come? Let's try to understand this implication. If c is a zero of a polynomial p of x, that means that p of c is equal to 0. But on the other hand, we know that p of c is the same as the remainder from the division by x minus c. Therefore, the remainder from this division is 0, which means that the divisor x minus c is actually a factor of polynomial p of x. Therefore, p of x is divisible by it. Now, to justify the backwards implication, assuming that p of x is divisible by x minus c, again referring to this equation, that would mean that r is 0. But if r is 0, therefore p of c is equal to 0, which means that c is actually 0 of a polynomial p of x. Therefore, these two statements are really equivalent. We really have if and only if statement. In the next example, for the given polynomial, fourth degree polynomial as stated here, we need to find the value of this polynomial at -3 using synthetic division and the remainder theorem. So first, let's use synthetic division. Okay, since we know that f of -3 is actually the remainder from the division by x minus -3, which is actually +3, then, in order to find this remainder, we can divide the given polynomial with coefficients 1, 5, 1, 3, -3 by the number c, which is -3. Okay, let's go through the synthetic division algorithm. 1 goes down, multiply -3, add, it's 2, multiply -6, add, -5, multiply 15, add 18, multiply -54, and add -57. So when we cut off the last number, this is our remainder from the division. Therefore, we know that f of -3 is equal to the remainder from remainder theorem, right? It's equal to the -57. Okay, we could also find f of -3 in different way. For example, just evaluate f of -3. That means plug in -3 to the polynomial and see how much is that. And we will see that this becomes exactly the same. +3 times -3 minus 3. So the first term is really 81, second is minus 27 times 5, which is 135, plus 9, minus 9, and minus 3. So these two are gone, and after adding the numbers, we end up with -57. So as you see, we have two different ways of finding f of -3. We could directly plug in -3 to the function and evaluate it, or we could use synthetic division and the remainder theorem, which states that the value of a polynomial at some constant is equal to the remainder from the division by x minus that constant. The next question asks us to factor this polynomial into linear factors if we know that -3 is a zero of the function. So knowing that -3 is a zero means that this polynomial is factorable by x plus 3. So if we want to find out the quotient from division of polynomial f of x by x plus 3, and then find out what's next, then we can use synthetic division. So start with listing coefficients 6, 19, 2, and -3, and divide it by the root -3. So bring the first number down, multiply -18, add, multiply -1, multiply, and we have 0. That's a confirmation that -3 is really a root. The remaining polynomial can be read from here, and it is 6x squared plus 1x and minus 1. Now, since this is a quadratic, we know how to factor it. We could try to guess the numbers if it's factorable, or if it's not factorable, we could use quadratic formula. In this case, we can probably factor it. So let's try. The last number must be 1 for sure, and we must have two different signs because the product is negative. The front numbers before the x, well, could be 6 and 1 or 2 and 3. Let's try 2 and 3. We fight for matching the middle term. The middle term comes from multiplying the inside, outside, and adding these two products. So the inside is 3x, the outside product is 2x. We want these two products differ by 1, and yes, they do differ by 1. So we want the difference to be positive, so this is positive and that's negative. Therefore, this product must be positive, so I need to have a plus here. This product must be negative, so I need to have a minus there. And yes, we already have the factored form. Now we can easily read all the roots of polynomial f. So the roots are -3 from the first bracket, -1/2 from the second bracket, and 1/3 from the third bracket. The next question asks us to determine the value of k, a parameter k, that will make this polynomial with k as a coefficient divisible by x plus 1. If a polynomial is divisible by this linear factor, then the -1 should be a root. So -1 is a root of p of x, meaning that p of -1 is equal to 0. So what we can do is to find out what's p of -1 by just plugging -1 there. P of -1 equals -1 cubed is -1 times 2, so it's -2, plus -1 squared is just 1, minus k plus 5. And this value should be actually 0 by remainder theorem. So what's left to do is just solve this equation for k. We can bring the k to the other side, and then we have 6 minus 2, it's 4 on that side. K must be equal to 4.